Welcome to the complete guide to neural networks. In this comprehensive tutorial, we'll explore everything from the biological inspiration of neurons in our brain to the mathematical foundations of artificial neural networks to real-world applications transforming industries today. By the end, you'll have a deep understanding of how these powerful systems learn and make predictions. We've organized this course into 10 comprehensive sections. We'll start by understanding what machine learning really is and how artificial neurons are inspired by the human brain. Then we'll dive deep into the architecture of neural networks, exploring neurons, weights, and layers. You'll learn about activation functions and why they're crucial. We'll walk through forward propagation step by step. You'll understand matrix operations that make it all efficient. And finally, we'll see how these concepts power real-world applications. Let's begin this exciting journey. Machine learning is fundamentally different from traditional programming. In traditional programming, we write explicit rules by hand. We give the computer data and our carefully crafted rules, and it produces a result. For example, to detect spam emails, we would write rules like if the email contains certain words or has suspicious links, mark it as spam. But machine learning flips this paradigm completely. Instead of writing rules, we give the computer data and the correct results we want. The learning algorithm figures out the rules automatically. For spam detection, we show it thousands of emails already labeled as spam or not spam, and it learns the patterns that distinguish them. This is the fundamental insight that powers all of modern artificial intelligence. The key insight is this: instead of manually programming rules, we let computers discover patterns from examples. This is far more powerful for complex tasks. Neural networks are inspired by the human brain. Your brain contains approximately 86 billion neurons. Each biological neuron has dendrites that receive signals from other neurons, a cell body that processes these signals, and an axon that transmits the output to other neurons. The connections between neurons, called synapses, have different strengths that determine how much influence one neuron has on another. Artificial neurons are inspired by this biological structure, but they're simplified mathematical models. They have inputs similar to dendrites, weights that represent synapse strength, a summation step that processes the weighted inputs, and an activation function that produces the output. While inspired by biology, artificial neurons are much simpler and work differently in many ways. They're mathematical abstractions that capture some key principles of neural computation. Remember, artificial neurons are inspired by biology, but they're not trying to perfectly replicate biological neurons. They're practical mathematical tools for computation. A neural network is organized into layers. First, we have the input layer where raw data enters the network. For example, if we are processing a black and white image that's 28 by 28 pixels, we'd have 784 input neurons, one for each pixel. Then we have one or more hidden layers where the real learning happens. These layers learn to extract features and patterns from the data. The first hidden layer might learn simple features like edges or corners. Deeper layers learn more complex patterns like shapes or objects. Finally, the output layer produces the network's prediction. For classifying handwritten digits 0 through 9, we'd have 10 output neurons, one for each digit. Neurons in each layer typically connect to all neurons in the next layer, forming a dense network of weighted connections. This is called a fully connected or dense layer. A neuron performs two key operations. First, it computes a weighted sum. This means multiply each input by its corresponding weight. Sum all these products together, and add a bias term. This gives us z. The bias is like a threshold that shifts the function. Second, the neuron applies an activation function f to z. This produces the final output of which gets passed to the next layer. These two steps, weighted sum and activation, are what every single neuron in the network does. It's surprisingly simple, yet incredibly powerful. When you have thousands or millions of neurons working together, weights and biases are the learnable parameters of a neural network. Let's understand what they really are. Weights represent connection strengths between neurons. They determine how much influence each input has on the neuron's output. A large positive weight means strong excitatory influence. A large negative weight means strong inhibitory influence. Weights near zero mean that input has minimal effect. For example, a weight of 2.5 amplifies the input by a factor of 2.5. Biases are threshold adjustment values. Each neuron has its own bias. The bias shifts the activation function left or right. This allows a neuron to fire even when all its inputs are zero. It fine-tunes the neuron's sensitivity to inputs. During training, the network adjusts both weights and biases to minimize prediction errors. This is how learning happens. Let's explore the three main types of layers. The input layer is the gateway where your data enters the network. It has one neuron for each feature in your data. For a 28 by 28 pixel image, that's 784 neurons. No computation happens in the input layer. It simply passes values forward. Hidden layers are where the magic happens. This is where learning actually occurs. Hidden layers learn to extract features and patterns from the data. They create hierarchical representations. The first layer might learn simple features like edges. Deeper layers learn more abstract concepts like shapes or objects. Having multiple hidden layers makes the network deep, hence the term deep learning. The output layer produces the network's final predictions. Its size depends on your task. For binary classification like cat versus dog, you need just one neuron. For multi-class classification with k classes, you need k neurons. The output layer also uses a task-specific activation function. Activation functions are absolutely crucial. Let me explain why. Without activation functions, something terrible happens. Multiple linear layers collapse mathematically into a single linear transformation. No matter how many layers you stack, it's equivalent to just one layer. The network can only learn straight-line decision boundaries. It becomes completely useless for complex patterns. But with activation functions, magic happens. Non-linearity breaks this collapse. Each layer genuinely adds new expressive power. Networks can now learn curves, circles, spirals, any complex shape. This enables universal function approximation. This is the key insight that makes deep learning work. Let's look at common activation functions. ReLU, which stands for Rectified Linear Unit, is the most popular. It outputs 0 for negative inputs and the input itself. It's fast to compute and works very well in practice. It's the default choice for hidden layers. Sigmoid squishes any input to between 0 and 1. It's useful for output layers when you need probabilities. Tan squishes inputs to between -1 and +1. It's zero-centered, which can help with optimization. The choice of activation function can significantly impact your network's performance. Forward propagation is how data flows through your network to make a prediction. Think of it like an assembly line in a factory. Raw materials, your input data, enter at one end. Each station along the assembly line represents a layer. Every station processes the materials and passes them forward. Transformations are applied at each step. Those are the activation functions. Finally, the finished product emerges at the end. That's your prediction. The key characteristic is that information flows in one direction only, from input through hidden layers to output. No looking back until we get to training. The algorithm is beautifully simple. For each layer, we do two things. First, compute Z, the weighted sum of the previous layer's activations. We multiply by the weight matrix and add the bias. Second, apply the activation function to get the current layer's activations. These activations become the input to the next layer. We repeat this process layer by layer until we reach the output. The final activations are your network's prediction. This is forward propagation, the foundation of neural network inference. Matrix operations are the secret to making neural networks practical and fast. Let me explain why matrices are so important. First, batch processing. Instead of processing one image at a time, we can process hundreds simultaneously using matrices. All examples are computed in parallel. Second, GPU acceleration. Graphics processing units are specifically designed for matrix operations. They can perform matrix multiplication 1,000 times faster than sequential loops. This is why deep learning exploded after GPUs became widely available. Third, clean and elegant code. Instead of nested loops iterating over each neuron and each sample, we write Z equals W times X plus B. One line of code handles an entire batch. Understanding matrix dimensions is crucial. The weight matrix W has dimensions neurons out by neurons in. The input matrix X has dimensions neurons in by batch size. Each column of X is one training example. The bias B is neurons out by 1. The result Z has dimensions neurons out by batch size. For example, if we have 784 input features, 128 neurons in the next layer, and a batch of 32 samples, we multiply a 128 by 784 matrix with a 784 by 32 matrix, resulting in a 128 by 32 matrix. Each column of the result corresponds to one sample in the batch. Matrix operations transform neural networks from a theoretical curiosity into a practical, scalable technology. Neural networks are transforming every industry you can imagine. In computer vision, they power image classification systems that can identify thousands of different objects. They enable object detection in self-driving cars, recognizing pedestrians, vehicles, and traffic signs in real time. Face recognition systems use neural networks to unlock your phone or find friends in photos. Medical image analysis helps radiologists detect cancer and other diseases earlier and more accurately. In natural language processing, neural networks enable machine translation between languages with near-human quality. Chatbots use massive neural networks to understand and generate human-like text. Sentiment analysis helps companies understand customer feedback. Text generation creates articles, stories, and even code. In healthcare, neural networks analyze patient data to diagnose diseases from symptoms and test results. They are accelerating drug discovery by predicting how molecules will interact. Personalized medicine uses neural networks to tailor treatments to individual patients. In autonomous systems, neural networks are the brain of self-driving cars, processing sensor data to navigate complex environments. Robotics uses them for computer vision and motor control. Gamma like AlphaGo defeated world champions by learning strategies no human had ever discovered. Drones use neural networks for navigation and object tracking. The applications are truly limitless. Neural networks are the foundation of the revolution we are living through right now. Congratulations! You've completed this comprehensive journey through neural networks. Let's review everything you've mastered. You understand the fundamentals of machine learning and how it differs from traditional programming. You know how artificial neurons are inspired by biological brains. You understand network architecture with input, hidden, and output layers. You know exactly how neurons compute using weighted sums and activations. You understand weights and biases, the learnable parameters. You know why activation functions are absolutely essential for non-linearity. You can explain the forward propagation algorithm step by step. You understand how matrix operations make it all efficient. And you've seen the incredible real-world applications transforming industries today. This is an incredible foundation. Where should you go from here? First, implement forward propagation yourself. Use NumPy to code the matrix operations. This will cement your understanding. Second, learn about backpropagation, the algorithm that trains neural networks by computing gradients. Third, explore modern deep learning frameworks like PyTorch or TensorFlow. These libraries handle the complex math and let you focus on building. Fourth, and most importantly, build real projects. Start with something simple like digit classification, then move to more complex tasks. There is no better teacher than hands-on experience. You now have the foundation to understand and build. Thank you for investing your time in learning neural networks. You now have the knowledge to understand and build. BI systems powering the future. Keep learning, keep experimenting, and most importantly, enjoy the incredible journey ahead in deep learning. Good luck! If you enjoyed this journey, don't forget to hit the like button and subscribe.